Now we want to solve some questions on magnetism, some common questions on magnetism, and as I do that, we'll also be learning one or two things about it. Now this one says what? That let's start from here. It says a method of demagnetization. A method of demagnetization taken from number 7 of that question. Yeah. The method of demagnetization is dash. A double stroking the magnet with soft iron in the northeast. Yes, we have ways of that. One is magnetization rather. So we have magnetization and we have what they call demagnetization. So if you want to magnetize, you use what? Using double stroking method. Double stroking method of the what? Double stroking the magnet with what? Soft iron. You can use what? Single stroke method. Single stroking the magnet with what? The north south. Single stroking the magnet with what? Soft iron in what? North south. Then you can also use what? Passing the what? The magnet through what? A DC. Through a DC. Or they will say what? Sometimes they can, like what they use here now, say placing the magnet in a solenoid, a bar solenoid. That means you have a solenoid like this connected to what? A DC. Then you pass your magnet what? Across the what? The solenoid, something like this. Then you drag it through the northeast direction. So, but don't forget that if you connect it to an AC, you demagnetize. So that is just that. You can also hammer in the northeast, north-south direction. Hammering in the north-south direction can also work. But if you want to demagnetize, you can apply what? Heating method. Heating. You can apply hammering in the east-west direction. Hammering in what? In the east-west direction. You can also use what? Vibrating the what? The magnet. Vibrating the magnet in what? East-west direction. Also, you can also use what? Passing the what? The magnet through where? Through what? An AC circuit. That means passing through the magnet through a coil connected through, let me put it, through a solenoid. Let me put that way. Solenoid. Connected to what? To an AC. Then also we can also what? Achieve that by what? Not forget the best method of what? Demagnetizing without affecting the magnet is what? Is this one, in case they ask you the exam. Now, why the best method of what? Or the method by which you can completely demagnetize magnet is what? By heating, whereby the magnet become red hot, and that heating is that most likely they destroy the magnet at the end of the day. When you use heating method is when you want to completely demagnetize, completely, that means 100% demagnetize magnet. Use one, but it's not the best method to use. The best method to use is what? Because we need the magnet to be reused again after use. So the actual the best method go for this. Right? If the best method of demagnetizing this, best method of magnetizing, use this one. Then when you want to completely do what? The most effective what? Ways to demagnetize, then this is most effective. That means to know what when something is effective means that you want to make it 100% most effective. This one is what? So that is just that. Now, another thing again you have to note here is that during magnetization, The molecular magnet in the magnetic domain align themselves in one direction. The smallest magnet is what we call the magnetic molecule. Magnetic molecules are the smallest magnet. And when they are what? Found in the magnetic domain, the housing of a magnet of where they reside is called magnetic domain. Now, in this magnetic domain, where they reside, there is bound to be what? Magnetization when they align themselves in one direction. But when they demagnetize, look at what will happen. They begin to move, the magnetic molecules begin to move randomly in the magnetic domain, whereby the effect of one cancel out the other. And when the effect of one magnetic molecule cancel out the other, they become demagnetized. You understand? They move randomly. And one way to make them move randomly, where the effect of one cancel the other and the magnet become what? Magnetized, is what? All this method. Then to make them align in one direction, it means that they have become what? Magnetized. And we check. DC is what? Allow current to flow in one direction. So therefore, it helps the molecule to what? Flow in one direction. So that is one way. So let's look at the option there. Option A is what? Double stroke method of no, that one is not in the northeast direction or north south direction. Right? B said eating the what? The magnetic bar red dot and allowed to cool east west direction. I think that one is correct. To demagnetize. I say method of demagnetization. So B is saying eating a magnetic bar red, eating a magnetic bar red hot and allow it to go east west direction. Oh, that one is correct. Placing the magnetic bar in a solenoid. That one is correct partially. You know, they're supposed to tell us solenoid in the world. You know, passing the magnetic bar. They can say magnet through what? A solenoid. That be connected to what? They did not complete it, but we'll take it like that. We'll take it based on we have very wrong one in your shop. No. Under the AC is what? The magnetization. DC is what? Magnetization. Then another one says what? Hammering the what? Hammering the bar magnet repeatedly in the north-south direction. Yes. Repeatedly. When you hammer, I think I did not write it. Hammering in the north. I think I mentioned it, but I did not write it. This one, you hammer in the east-west. It's different from hammering in the what? So when you hammer in the north-south direction, you can repeatedly you can achieve magnetization. So the answer is B to the question. Now let's go to what? Calculation there. The calculation. Now when an electron enters into an electric field, it forms a circular path. When an electron enters into a magnetic field, it forms a circular path. And because take note of that, when an electron enters into a magnetic field, what kind of shape does it form? It forms a circular shape. And that's why we say with centripetal force, at that point we balance the magnetic force at that point. Because we have a question to answer there. Now look at the board. This one is not too common in some O-level. So this one will have what? This one cancel this one, mean one. And MV over R equal to what? QV or QB. Now, if I want to solve this one now, what am I going to do? Is to what? MV is equal to what? QBR. So now, what they say we should find? Look at the question here. It said, what is the mass of number 8? What is the mass under magnetism? What is the mass? What is the mass of a 4.5 times 10 by what? Minus 8 column. What is the mass of what? Of 4.5 times 10 raised to power minus 8 coulomb charge particle moving in a circle of radius 20.5 centimeter on a speed of 4 times 10 power 7 meter per second in the vicinity of 140 microtesla magnetic field. This question is very interesting. Now, what we are going to do now is that because it enter into a circular path, and for example, for the electron to maintain that circular path, it must be under the influence of a centripetal force. A body will continue moving in a circle with the help of what? Because that is the force that holds the body in the circle, that can hold the particle in the circle. So that is balancing the magnetic force that the electron comes with. So that means that the charge comes with this charge. It's not an electron now in this case. So now in this case, now we want to find the mass. How do we look for the mass? Since you know your formula, you can find the mass from even here. Because it's mv equals to what? QBR. Now don't forget that mv is also known as what? The momentum. In case it asks you to find momentum of the charge, is QBR. Momentum is equal to what? Charge times what? Magnetic field times radius. So in this case now we can say V is equal to what? QBR over what? Or mass equal to QVR over V. So in that case now what we want to have now is that mass, let me change my marker, mass is equal to what? 4.5 times 10 raised to power what? Minus 8, that is charge, times B. What is our B there? 140 micro times 10 raised to power minus 6 Tesla. No need to then this 140. Then our R is what? Don't forget, if R is equals to what? 20.5 centimeter, you can convert to meter by what? Divided by 100. So that will now give us what? 0.205. So in that case, now this one has got 0.205. You divide by what? What is velocity given to us? They give us velocity of the charge. 4 is there. Velocity of the charge is given is what? 4 times 10 is per what? 7. Now what we want to do now is that this one will go as what? Minus 7. So what we want to have is this multiplied by this plus will give us, let's say 45. This 0, let us shift the decimal point. 45 times 140 times 0.205 divided by 4. Then this one is what? 10 raised to power minus 8 times 10 raised to power minus 6. Then times 10 raised to power. If this one go up, it will become minus 7. Because you cannot have this here. Then this one will give us approximately what? This one will give us 2 year 1, 2 year 2 year 2, 2 year 70, 2 year 1, 2 year what? 35. So 35 times this will give us 45 times 35 equals 25. Carry 2, carry 3 rather. 20 plus 15, 35. Then 35 plus 3, 38. Carry 3, 12 what? 15. 15 what? 1585 times 0.205 times what? 10 raised to power minus what? Minus this minus 40 minus 21. If you multiply this one now, this 5 shift decimal point, you are supposed to have approximately 3.2 something times 10 power. Then this one is 32 times 10 power minus 20, which is approximately what? 3.2 times 10 power what? But this minus 21, then minus 20. This one is supposed to have what? What is supposed to have? You can copy. So This one is what? No, us. Okay, minus this minus 22. Yeah, this one will be minus 21. It's correct. What you just need to do is just what? If you multiply this one and this one will give us 3.2. This one will give us 3.2. Except probably there is a mistake somewhere here. Because if 2 here is true, 2 here in 170 is okay. This one is 1.4.5, sorry. Then 2 here 35. Then 35 this one should give us 1.5, something like this. So that's what I'm supposed to have. So 35 times 4.5 will what equal 158.5 times 0.2025. 205 rather. And you're supposed to have that as your answer. You can also confirm it as you are solving now before we move forward. Now, and if you have that as your answer, that should be option D as your answer. D should be our answer there. G, which is 3.2 times x power minus 21. So that is just that. So you can press your calculator to confirm it more and more. Now, that is settled already. Now, this one says that what? Let's take this one. It says when we have a diagram like this, look at the diagram. Now, this diagram now, we have something like this. I have a question like this. They said what? They said in the diagram above this diagram, they said shows a current, carrying wire between the poles of a magnet. In which direction would the wire move? In the diagram above shows a current carrying wire between what? Between the pole of a magnet. In which direction would the wire move? A, into the wire. Now, what I want to do, there are two ways. You can use flaming left hand rule. Flaming left hand rule, you can use to attend to it. I think I use my shortcut for it. Now, this is the flaming left hand rule is what? This one, it says that when your first finger, second finger, or middle finger and your thumb are mutually perpendicular. So when your first finger, your second finger, and your thumb is mutually perpendicular, what it's saying is that the first finger represents direction of field, second current, while the thumb is motion. Thumb is what we indicate direction of motion of force. So that is what it's saying. That is the definition. That flaming item says that when the thumb, the first finger, second finger are mutually perpendicular, the direction of the first finger is direction of field, second finger is direction of current, third finger, the thumb is direction of motion. So it will remember, what do you remember? Second. What do I end with? Current. Second. Current. First, everything is first, field. So like that. Now, if I want, this is field now. Now, if this one is direction of field, which is up, direction of field, this is direction of current. Let's turn it like this now. Now, where is it going? Out of the paper. If you check now, this is direction. Look at the direction of field here. Look at it, north, going from north to south. So, direction of field is like this now. Then direction of current is what? Down. Where is the finger, the thumb pointing at? Out of the paper. So the answer for the motion of the word is out of the paper. And now I want to ask you a question now. Let me change the direction of the current. If I have it like this now, let's say I have a diagram like this, north, south. I have something like this. Where will the direction of motion be now? Yes. into the paper, abi? It will be into the paper because it will be like this now. Current, this field, it will be into it. Look at my pointing into the paper. So that's how to know that, and that is clear. So answer is what? Out of the paper for this. This will be into the paper. Please take note of that. Very important question that always confuse a student, and I want you to take note of that. They say two inductors of inductance. Two inductors of inductance, 4 Henry and 8 Henry, are arranged in series, and a current of 10 amperes passed through them. Two inductors of inductance, that's 4 Henry and what? 8 Henry, are arranged in what? In series, and a current of 10 ampere is passed what? Through them. It's passed through them. So what is the energy stored? In them. Energy stored in them. Now, this one now is that, don't forget, there are basic things you need to know here. If you have what? Now, if you have currents, flowing through inductor with what? That are arranged in series. Let me just show you something. Now, if you have inductor, another inductor in series, L1, L2, L3. Now the total inductance is what? L1 plus L2 plus L3. The same thing with what? Resistance in series. Don't forget, resistance in series is same thing as what? Resistance. If you have what? 3 resistance in series. Now I say R1, R2, R3. The total resistance is what? R1 plus what? R2 plus what? But if I have capacitor in series, let's say C1, C2, C3. What would have been now? Total resistance capacitor 1 over C1 equal to what? Plus 1 over C2 plus what? So that is what we have here. The energy that is stored here is heat energy. The energy here is what? I square RT, total energy. We want to calculate the energy that we can calculate that is stored in the coil is what? 1 over 2 Li square. While the energy that is stored here is what? 1 over CV square. So this one store electrical energy, which is 1 over CV square, or 1 over what? 2 QV. 1 over 2 CV square, or 1 over 2 QV, or 1 over 2 what? Q square over C. So this one now, we can write it as what? This is heat energy. This one is also the same thing as ITV. It's the same thing as what? QV. So some people always make QV with what? Half QV. Half QV is electrical energy. QV is heat energy. So why half Li square is what? Magnetic energy due to magnetic what? Energy stored in the coil, which is magnetic energy. Now, so that is just that. Now, in this question, now we have what? 4 Henry and 8 Henry being connected in what? In series. So if you want to get the total now, on what we have there, is just for us to what? Just for us to what? Add them together to get total. So we have L total is equal to what? 4 Henry plus 8 Henry. What do you have? 12 Henry. Have you? So now, energy stored is equal to half what? Li square. Now, I is already what? What is the current there? Current is already giving us what? 10 ampere. This L total. So this L total I want to use here is not just L, ordinary L total. So I would have half times what? What is our L? 12 times what? 10 square. So this one will cancel this one. I would have 6. So 6 times what? 100 is what? 600 joules. That is the answer there. So please write. Now, we want to solve this question. It says, which of the following may be used to measure alternating current? We have Roman figure 1. We have moving what? We have moving coil ammeter. Now, moving coil ammeter, they are used to what? They are used to measure what? Used to measure what? DC. Not only that, also we have also an instrument called DC ammeter or DC balance meter or DC ammeter. You understand? Moving coil what? Ammeter is used to measure DC. So let's go to number 2, Roman figure 2. We have moving ion ammeter. Moving ion ammeter. They are used to what? To measure what? AC and DC. Now AC at low what? Low frequency. And DC also. So DC. So DC means direct current. Don't forget DC is what? Direct what? Current. AC means what? Alternative. Or DC means direct circuit. Direct current. And DC means what? Alternating circuit. If I should ask you now which instrument or which device uses AC only, example is what? Transformer. Transformer is a device that uses what? AC only. Convert what? AC of one voltage to another AC of another voltage. Transformer. Why induction coil uses what? DC only. Convert DC what? From a low DC voltage to high DC. Convert what? Used to what? To what? Produce what? High DC voltage from a what? From a low what? DC voltage. But this one now can be what? Can either what? Produce high DC voltage from low DC voltage, that is for step up, and can also what? Use it to produce low DC voltage from low AC voltage from high AC voltage. Can use to produce high AC voltage from low AC voltage, that is step up, or produce what? Low AC voltage from what? High AC voltage, that is step down. So that means that's why they are used for what? For changing what? Changing what? Voltage. Changing voltage. AC voltage. Now, the next one is this. Roman figure 3 that they gave us is what we call what? Hot wire ammeter. Hot wire ammeter. Hot wire ammeter is an instrument that is used to measure an ideal what? AC. Also, it can be used to measure what? DC also. But note, this one can never be used. Moving coil ammeter can never be used to measure what? AC. Example of a moving coil ammeter is what we call the galvanometer. Galvanometer. Don't forget that galvanometer is also called milliammeter. And when you talk about galvanometer, they can convert galvanometer to ammeter by connecting what? Look at this is a galvanometer now. You can convert them to ammeter by connecting shunt in parallel. I hope you remember. Connecting shunt in parallel with what? Will make you what? A shunt. What is a shunt? A shunt is a low what? Resistance component. Yes, sir. Are they resistant? Yes. Shunt are resistant. So they are resistant. The question is what kind of device is a shunt? It's a resistor, but they are low resistor. So if you connect them in what? So you convert what? Convert what? Galvanometer to what? Ammeter by what? Connecting what? Connecting what? Shunt in what? In parallel. But you can convert them to what? Galvanometer can be converted to what? To voltmeter by what? Connecting what? Multiplier in series. Please take note of that. That is to say that this is what? Galvanometer. You connect this is a multiplier. So this one will now act as what? The multiplier. What are multiplier? Multiplier from the name, it implies that there are what? High resistance component. High resistance what? Component. So when you connect those are questions in the exam. If they don't call it galvanometer, they will call it what? Milliammeter. Why do we call them milliammeter? Because they are used to measure minute current, very small current. That's why we require what? Because of their resistance is very high. You understand that? Galvanometer have a very high resistance, so they could take only what? Small current. You understand that? So in this case now, how do you make them measure a high current? If they ask you, how can you make a milliammeter to measure high current? By connecting what? By connecting a shunt in what? In parallel. How can you make a milliammeter to measure a voltage? You understand that? To act as a voltmeter. We know that voltmeter are what used to measure potential difference, which you call the terminal PG across a circuit. So how can you make them to measure it? If by connecting a what? A high resistance in series, which is a multiplier. So just take note of that. We have a calculation that we'll do there, but we are coming to that. So they say what is the answer to this question now? They said what? Roman figure 3 is hot wire ammeter. Then option A says what? 1 and 2. Option B say 2 and 3. C say 1 and 3. D say 1, 2, 3. So the answer is what? 2 and 3. It's only 2 and 3 that can measure what? AC and DC. Even though the hot wire ammeter used to measure an ideal AC, but at least you can do. When I say an ideal AC, that is something that is not too real. You understand? That's why most of the times, if you want to measure AC properly, the best among them is what? Even you can measure AC at low what? Frequency. Can you see that? So that is just how it plays. Now let's look at this question. It says what? That which of, okay, we have answered that one. It said what? Which of the following is not a part of a DC electric motor? DC electric motor. DC electric motor. We have A. We have armature. Armature is part of it. Armature is also in the AC dynamo. AC dynamo. In fact, we have AC dynamo or AC generator, and we have DC generator. I'm coming to that one. But let me list this one first. Now, what are the components? We have the armature, we have the what? The field what? Windings, or what we call the what? The field motor. The field motor. We have the field motor. We have the what? The commutator. Commutator. Then we have what they called what? Transformer. No, we don't have transformer in that way, but we have what? We don't. Transformer is not part of what? Of DC. We have what? Coils. The coils. We have the brush, the carbon brush, carbon brushes, and all that. So that is what are the things? Those are the things we have there. We have the what? The spindles. So that is for DC motor. No. Now we don't have transformer. We can even have split ring. Split ring is also known as, we can call them the commutator. In this case, they are what? Don't forget that DC motors convert what? DC electric motor convert what? Motor. Use what they call a shortcut called MM. MM is the shortcut to remember. What does it mean? Well, electric motor convert what? Electrical to what? Mechanical. Electric motor convert electrical to mechanical. But for dynamo are what? Generator. This one has armature. This one also have what? An armature. Then this one has what? A slip ring. This one have what they call split ring. Then this one has what? The carbon brushes. This one also have carbon brushes. Then this one has what they call what? They have the powerful magnets. Magnet. This one also have powerful magnet. I create a strong field for them. Now, the question I want to ask now is that if you are to design an ADC and you mistakenly design an AC, what do you do to replace? What do you replace it with to convert it? You design DC, and the contract they gave to you was to design an AC generator, and you mistakenly design a DC generator. What to do? What will you require to change in this what manufacturing of this DC generator to become an AC? It just what? To remove the what? The split ring and replace with what? Slip ring is part of the question you should expect on that is very common in this case. So you replace it. So transformer is not part of it. Transformer is not part of electric motor. This one, calculation. Now we know that what the formula for force is equal to BIL sin theta, or F equal to QVB sin theta. Now F is equal to 0 when theta equal to what? 0. That means whenever the field is parallel to the what? To the length of the field, we said what? It is what? But anytime the field is also what? Parallel to the velocity of the field, the field, magnetic field is parallel to the field, we say theta equal to what? 0. But anytime the what? That means V is parallel to what? B. But anytime your velocity is perpendicular to B, we say theta equal to what? 90. Anytime, and don't forget, this is the minimum force you can have when what the field is what? Parallel to the what? The length of what? Of the field. Make note of that. But when the B is perpendicular to the length, theta becomes what? 90. And this is maximum what force you can produce. What is the maximum force? BIL. What is the maximum force here? QVB. Because if you put 90 here, sin 90 is what? Is 1 now. So in that case, since sin 90 is 1, you just what? Put it there. Now, what we're going to do now is to solve problems. So this is maximum force. Maximum. What about if it's at an angle? Then you can use the angle, you can use the formula there. So now let's see. Let's say Don't forget dynamo before I leave there. Dynamo convert what? Mechanical to electrical. Dynamo convert mechanical to what? Electrical. Dynamo convert what? Mechanical to what? Electrical. So if you can remember what M is what we second to last, then you just remember that it starts from mechanical to what? To convert to electrical. It's an opposite of motor. It's an opposite of motor. Now they say the force on a current carrying a conductor, the force on a current carrying a conductor in a magnetic field is greatest when the dash is greatest when the dash A is greatest when the dash A. What is our A? They said what? When the conductor makes an angle of 60 degrees with the field. No, is that correct? No. But when it makes 60 degrees with the field, it is what? It is about root 3/2 thereabout. No, it's not correct. B, when the force is independent of what? Angle between the field and the conductor. No. Don't forget, this one is the length of the conductor length. So C said conductor is parallel to with the field. No. When the conductor is parallel to the field, that is this case now. Conductor is separable. When conductor is at right angle with the field, yes. When the conductor is at what? That is, the conductor itself is at what? That of length L is at right angle to the field. So in that case, it will be maximum. When it's parallel, it will be zero force. Don't forget that very, because they are easy. Now this one says the device used to measure the angle of dip is dash. Is what we call what? The dip circle. The angle, the device used to measure the angle of dip is what we call the dip circle. Now don't forget that in a what? We have angle of declination and angle of inclination. Now look at the board. This is the earth. Let's say this is the earth. Now we have the what? Let's say we have what? The magnet resting on the what? The magnetic meridian of the earth. Let's say this one is meridian what? North, because the south will rest on the north, while north will rest on the what? South magnet. Now this is the equator of the earth. Now we draw the what? The geographical what? Meridian north and south. This will be what? Geographical what? Geographical what? Meridian what? North. While this one will be what? The geographical what? Meridian what? Meridian south. Now this angle between the what? Between the geographical meridian and magnetic meridian is what we call what? Angle of what? Of declination. Angle of declination. Or what we call what? Angle of what? Variation. Angle of variation. Now the angle between there is what? Now this is the equator. Don't forget, I told you this is the equator. This is like the earth now. There is an horizontal line that is what? This is called the horizontal line of the earth. The horizontal line of the earth. Now this is the horizontal line of the earth. The horizontal line of the earth. So now, don't forget, In the exam, they can ask you, where is the compass needle always located? The compass needle is always found along the what? The meridian of the compass needle. What is the compass needle used to measure? To measure the what? The direction of magnetic field. Don't forget that a band magnet what? Has the north and south pole. That means a magnet always exists as a dipole, not like what? Monopole. Question I ask you. Now, when you keep cutting a magnet, you keep having what? The north what? South pole continuously, the north and the south pole. That's what you keep having. And when you have a magnet like that, the strength of the magnet is located at the ends of the magnet. Don't forget, the strength of the magnet is located at what? At the ends of the magnet. So when a magnet is suspended, it comes to rest at the what? The magnetic, it comes to rest at the what? The meridian of the earth. The magnetic meridian of the, don't forget, the earth itself is a field. Earth is what? Is a magnetic field. The earth itself is a magnetic field. It's a magnetic field. The earth itself is a magnetic field. So in that case, that there is an angle here called what? Angle of deep. This angle of deep. Well, what we call what? The angle of what? Inclination. Angle. So in the exam, don't say the geographical meridian and magnetic meridian does not coincide. You know what I mean by coincide? Meeting. Because they always make that mistake. They will say the two of them always meet. They can never meet. The only angle between them is what? Because if they meet, there will not be angle of what? Declination. And this angle is used to measure the location of a particular place. So if you cannot have an angle of declination, you cannot have the true compass of the earth. So you cannot know the true location. So in this case now, the angle of declination will be known, which is the angle of what? Between the magnetic meridian north and what? Geographical meridian north, or the angle what? Between what? The compass needle and the geographical meridian south, or the what? The magnetic meridian south is what? Magnetic what? Meridian south, and the what? South, and the what? Geographical meridian south. In fact, the earth field is located here. They can say the angle between the earth field and the what? Geographical meridian what? South, or geographical meridian. Don't forget that the compass needle is used to measure the what? The magnetic field of the earth. The direction in which the compass will point is the direction of the field. So it helps us to know, it helps us to locate the direction of the field. Are you going to see that? So that is how it works. And don't forget, I told you that a magnet is concentrated at the end of the magnet. Now, note this again, very important. You must understand that there are two types of magnet. We have the permanent magnet and the temporary magnet. The permanent magnet is what we call the what? A good example of that is what? Steel. When we have a temporary magnet, which we call the what? The iron. Iron what? Why we call the temporary magnet that what? Because they are easily magnetized and easily what? Demagnetized. So the softer the iron, the better the magnetization and demagnetization. So the softer the iron, let me use that English. The more they are soft, the better the what? The magnetization and demagnetization. This one is what? It's what? Not easily what? Magnetized and not easily what? Demagnetized. They are made up of what? Two what? The iron and carbon. How do you know? Iron and carbon. And that's why iron now is what? Want to release the what? The magnet. But the carbon itself does not. It's not a what? It will not allow the magnet to be released on time. You understand? And if you want to do an experiment, to test for what? Magnetization, or to magnetize a magnet and to do an experiment on the magnetization, the best magnet to use is steel. Because using iron now, by the time you go through the process and do it now, because it will lose its magnetism. It will frustrate the what? The person doing the experiment. So it is advisable in performing to test in making magnets. Steel is the best option. You use permanent magnet to make magnet. And don't forget to make what? Electric bell. We use iron. In using electric, because electric bell will need the magnet to be demagnetized and easily magnetized. In electromagnet, we call them electromagnet. In use, it is used in electromagnet. Please take on that. It is used in electromagnet. Let's take some questions. So, angle of dip, don't forget, angle of dip is the angle between the horizontal of the earth and the what? And the magnetic meridian of the earth. Is the horizontal of the earth and the magnetic what? Meridian of the earth. So, angle of dip is what? Is 0 at the equator and 90 at the pole of the earth. Angle of dip is what? 0. If I rotate it here now, you understand now? It will be 0. The angle of dip will be what? 0 at the equator. When you take it to the pole of the earth, it will become 90. It become 90. So take note of that. It is 0 at what? Equator, and what? 90 at what? At the pole. 0 at the equator and 90 at the pole. And don't forget that what? When a magnet is suspended in the field, they repel each other like pole repair, while unlike pole attract. Look at it. This is like pole. They repel while unlike pole attract. This is it. Look at it. And when they repel, the arrow is going outward. Please don't mix it up. When they repel, because when they are now attract, when they repel, when they are south-south, the arrow go inward. The arrow go. If they are not interested in, they know that you know that it repels, but the major factor is how do they repel? Is the arrow going inward or outward? When the arrow is going outward, it is what? Not north. Then this is called the neutral point. Neutral point. This is called the neutral point. Then if the arrow, if the what? Let's say we have this south-south. Let's say we have north and south, they will attract. That's why we say unlike pole what? Attract, while like pole repel. This is it. They will attract, starting from the way? North. So the direction of the field is always from the north to the what? To south. This one we call neutral point. Why we call it the neutral point? Neutral point is the point where the magnetic field is equal to 0. Where the magnetic flux is what? 0. Where there is no force. Neutral point. So that is what we call a neutral what? Point. So you can write. Now let's solve this question. The question says that navigation on the sea is made easier when the angle of dash, A, declination is known, B, inclination is known, C, dip is known, D, incident is known. I think that answer should be what? Declination. I told you to navigate to locate. We use what? Angle of what? Declination. So the answer to what? To that one, when I was explaining earth field, is what? Declination. Angle of declination. So now the next thing they say we should do now is that. Now, first of all, before I go to the next thing, look at what is on the board now. Now, this is two parallel magnets in which my poles are opposite. Unlike poles are set in parallel. Two magnets. This one is parallel to this one, but their poles are unlike poles. So this is what we have. We have only one neutral point. One neutral point. Please remember that. Neutral point. One. That is what I want you to note there. That is for this one. It has only one neutral point. What about this one? When they are set in parallel, two magnets are what? Are placed in parallel, and their north pole are aligned. They are not opposite pole. Their poles are in alignment and they are parallel. It will have what? Two what? Neutral points. So one is here, one is here. Now, when the south is facing up and north down on the earth surface, it has only what? Two neutral points. One at the down, one at the up. There are two different things entirely. When the north is facing up and south is facing down, we have only what? Two neutral points, but by the side. But when the south is facing up and north is facing down, this one, north is facing up, south is facing down. North facing up, south facing down, we have it by the side. South facing up, north facing down, we have it up. Now, this shortcut I just show you now, this shortcut I want to show you now, Clinton cross down to southwest, meaning that it means that for clockwise, this one means for clockwise, this one clockwise into the paper, then that means that if I'm moving, like for example now, look at the board, I'm moving into the paper like this, like I'm moving into, like going down. Now, if the current is going down through the wire, what happens? Look at we use what? Flaming right hand rule. Right hand rule means that the direction of the what? I mean, not flaming right hand rule. Right hand rule is different from flaming right hand rule. Flaming right hand rule is to determine the direction of induced EMF. Flaming right hand rule is used to determine the direction of induced EMF. While flaming left hand rule is to determine the direction of what? Of force or direction of magnetic field. Flaming right hand rule is to determine the direction of what? Induced what? EMF. Don't forget. Flaming left hand rule is what? Used to determine what? The what? Direction of what? Of magnetic field or force. Flaming left hand rule is what we call the motor rule. While flaming right hand rule is what we call the dynamo rule. Motor rule and what we call what? The dynamo rule. The flaming right hand rule, Fleming. This is my Fleming right hand rule. Right hand rule is what we call the what? The dynamo rule. While the Fleming right hand rule, the Fleming what? Left hand rule, which I used to what? I've used it to solve already. Left hand rule. I told you that what? Direction of the thumb is direction of motion. Direction of the first finger is direction of field. Direction of the second finger is direction of current. I've used it. That is Fleming left hand, which you call the what? The motor rule. That is another name. That force. When they say force on the current carrying conductor, that's what I'm talking about. Fleming left hand. Force on the current carrying conductor, which is this force, F equal to BIL sin theta. This is force on the current carrying wire. While force on the charge is QVB sin theta. Force on the charge carrying what? In the field is what? This one. Now look at the board. Now when you draw clockwise into cross, now if I draw something like this, now look at the board, I draw cross like this, in between two lines. Now it means that current is going into, and it means cross. So that means the example of that is this one. Now look at the current. Current is going down. Now in right hand rule, which is different from Fleming right hand rule, the direction of your thumb is direction of current, while the direction of your coil finger is direction of field. So if I put my thumb here, my thumb is going down. Where would the field be going? Going what? Clockwise, Abi? So that means direction of field will now be like clockwise. And that's what I'm showing you. That if the field is going down, that means if the what, the, as you call it, the, if it's moving clockwise, that means clockwise what? It means it's what? The field is going clockwise. The current will go into the paper, which is showing cross. So if I show you cross like this, what does that mean? It means the field will go what? Clockwise. If I show you dot, dot is what? Showing that the field is going out. That is this one. Dot, anytime you see dot like this, it means the same thing with this. Cross means the same thing with this one. So if the current is going like this up, yes, look at your finger now. Let's see. Where will the current going? Anti-clockwise. Going anti-clockwise. At it, going anti-clockwise. You can turn your finger, look at it. So anti-clockwise. So that's it. Now, I've explained the direction of field now. Let's go down. Cross down to southwest. Southwest. Cross down to southwest. Now, anytime you are moving clockwise, it means direction. Not forget, south is clockwise, north is anti-clockwise. Look at it now. Direct clock, by using clock rule. South is what? Clockwise normally. Look at it now. If you see, they will write like, why north is what? Anti-clockwise. North is what? Anti-clockwise. Why south is what? Clockwise. So, once you go down, current is going down, the field must move what? This is clockwise now, abi? Then this one is what? Anti-clockwise. Then, the resultant of the field what? Will face west. Where is the west? If I draw my what? What is this one is what? North, east, and what? West. Abi? Look at the word. If you leave this field for a while, the resultant of the field will face what? West. It will face west. But what about what? If the field is what? Going what? Towards the what? That this one will not be what? Anti-clockwise, abi? This one will not be what? Out, abi? This one will not be what? Dot, abi? This one will not be dot. Then this one will not be up, abi? Then this one will not be what? To what? North what? East, abi? You know northeast? That's what is happening here. If you draw the what? The direction of the field, after some time, this field now will produce its resultant what? Field, magnetic field will face towards the what? The east. Why the resultant of this one, the resultant what? What? Magnetic field will face west. Because there's always a resultant that what? Because the earth will produce a resultant on it. Don't forget that what? Magnetic field is a vector. It's a vector just like force. So there's always a resultant in the field that will be created. So that is what is happening here. Now let us quickly what? I've explained this. Let's quickly look at this the conversion of galvanometer to ammeter. Now they said a galvanometer calculation here. A galvanometer to ammeter. Let's quickly look at it. So don't forget that when what the field is going down, the current move and field move. When the current is going down, field move clockwise. When the current is going on, field move what? Anti-clockwise. Downward current what? Clockwise what? Field. Upward current anti-clockwise what? Field. So cross is for showing that the current is going down. Dot is showing that it's going up out of the paper like this. And this one, when you show down, it means that it's moving anti-clockwise. I've explained that now. Let's see. A galvanometer of resistance of 20 ohms. 20 ohms is to be what? Provided with shunt such that 1/10 of the whole current in a circuit passes what? To the galvanometer. So the resistance of the shunt is dash. The resistance of the shunt is dash. The resistance of the shunt is dash. Now, what we are going to do now, look at the board. Now, the shortcut I will give you here is this, before we go, is that when you have a galvanometer, I think I will go to stop here so that after this calculation so that we can go and test. After the what? Now look at the galvanometer here. Now this galvanometer now is we connect shunt in parallel to it. But now the galvanometer of resistance, what is the resistance of the galvanometer? 20 ohms, is to be provided with a shunt that is 1/10 of the whole current. That means if the current is what? Is this one? That means you can be provided with a shunt such that 1/10 of the whole current in the circuit is to pass through the galvanometer. That means if let's say current, the whole current is I. You see this technical question? Then 1/10 of it is to what? You go to what? How many will go here? 9/10. How do we get it? If one current is now what? The entire current. If 1/10 goes here into the galvanometer, what will go here to go, because they will split. When they get to this place, they will split. Some come here, while some what go there. So 9/10, you remove 1/10 I from 1 I. That one 9/10. And they gave us the what? This one to be what? 20. Then I say what? Then I say what do you say? The resistance of the what? Of the shunt. That's what we are looking for. Now, don't forget, in electricity, when two resistors are connected in parallel, they have the same voltage. So the voltage of the shunt of the galvanometer is the same as the voltage of the shunt. So VG equal to what? VS. Note that. Then number 2 is that what? Since they are equal now, what we are going to do now is to what? Is to say IG times R what? G, which is because voltage equal to IR, then IS equal to what? RS. See now. So what is IG? IG is what? 1/10 what? I. Abi? Then times what? 20 is equal to what? What is IS? IS what? 9/10 I times what? RS. What? How do you find RS now? RS is what? This one will cancel this, Abi. So what we're going to have now is that 10 can cancel what? 10. It's not true. So we're going to have what? 20 equal to 9 RS. The Bible says by 9. What do you have? So RS equal to what? 2.22 ohms. 2.22. And if you check, you see that the value is small. The value is small. So your value for resistor must be smaller than, if it's bigger, you know that you solve, what you are solving is different from what you are supposed to do. Because everything that you are doing theoretically must align with what? With practical applications. Must apply what? Practically. So this one is 2.22. Now we solve one more on this. Yes. Okay, let's take another question on calculation on galvanometer. Calculation on galvanometer. But this time around, let's see another type of question. This one is a little bit technical. They said what? Okay, I think we are having only one question on galvanometer there on that particular. But take note, they say when a transformer, there is a question here. This is a transformer. I don't have enough question here on galvanometer, but let's see this one before or what. Now look at this question. This is AC. This is a transformer. Now look at this transformer. This is a load. They ask a very technical question here. Now the number of turns is proportional to what? E. Abi? Now induce EMF, the EMF. But look at the board. You see it? When a transformer has more secondary windings, that means there are more secondary windings in this case now. Secondary windings. That means that is what is a step of transformer. Now has more secondary windings than the primary. Hey, that means when transformer has more secondary windings than the primary, its A option has smaller secondary current. I think that one is making sense. Don't forget that the number of what turns is inversely not what current and directly not what induce EMF on the coil. So in that case now, I think that one is making sense. It has smaller current. B say it has greater power. No. C say it's a step down. No, it's a step up. D, it increased the total energy output. No. Total energy output is always smaller than what? Don't forget. No matter what, if the IS and VS is what? The power what? Output. Then IPVP is power input. The worst case in an ID transformer, the two of them will be equal. That's when NP over NS will be equal to VP over VS equal to IP over what? No, IS over what? IP, because they must be inversely. Okay, look at this question. They say the transformer has a primary what? You want to use that function now. Quickly. A transformer has a primary what? Coil with what? 500 tons. 500 tons. And secondary coil, if you know this question, you can be solving alongside me, with what? 2,500 tons. When the what? The voltage inputs in the primary coil is 120 volts. The output is dash. So they want to say the output voltage. Don't forget that this is the this is the secondary one. Secondary windings. This is the what? Primary windings. The voltage here, this is the what? Primary voltage and secondary voltage. The voltage, the secondary voltage is what? Is the voltage produced across the load. This is the load. I hope you know. Now, that is the load. This is the AC itself, AC supply. So the AC supply is connected to the primary windings, while the load is connected to the what? The secondary windings. So in this case now, if I want to solve now, I will use this formula. These two formula is what I will use because every parameter is given to me here. Look at it. So I will just say the word. What is my secondary primary windings or primary turns? 500. What about secondary turns? 2,500. What about the primary volt? The primary what in the primary coil is what? 120 volt. What about the secondary? Secondary is the output. That's why they want to use this statement to deceive. Because if they say find the secondary voltage or secondary PD, you will know. They want to know whether you know the output. Here is the output, and here is the what? The input. You understand me? So in that case, now don't forget that a transformer has what? Two what? It has core loss and coil loss. Coil loss and core loss. Yes, it has two kind of losses. Now, look, listen to this. Go and watch my video on transformer. So I don't have time. NP over what? NS equal to VP over VS. So I'll put the value there. What is my NP? 500 over what? 2,500, Abi? Now, this should be a step up, Abi? So over what? 120 over VS. Cross multiply. If you cross multiply, we are going to have it as what? 500 times what? Vs equal to 1000. That means 120 times 2500. If I multiply by 500, this one will cancel this one. I want to have it. So this one means 25. That is what? 6,000. 600 what? Volt. So that will give us our final answer there. So that is the final answer. That is where we are going to stop for today, and we have exhausted all the questions we have in what? Magnetism. I believe you enjoyed the class. Please, if you enjoyed it, you are supposed to what? Click the like button and also what? Subscribe. And I believe that more will be coming your way. I am Engineer Halide. Remain blessed. Thank you. God bless you.